All right, guys, here we go. So I'm going to throw some kind of a curveball at you guys. You probably recognize it, but it's been a long time, so just try to relax, try to breathe. What we're going to be doing is simplifying some stuff, but it's going to involve rationalizing the denominators. Okay, so remember that's where you can't have a denominator that has a radical in it. So remember when we had here, let me show you something. If we had, oops, hang on 2 seconds. If we had something like this, like the square, like 5 over the square root of 2. Remember, you can't leave it like that. So what did you have to do? You had to multiply by another square root of 2, right, over the square root of 2. And then so you end up getting 5 square root of 2. And then whenever you have 2 of those, you get just the 2 under there. What we're going to be doing today is more like this. If I have like 5 over the cubed root of 2, okay, well, I'm going to need to multiply by another cubed root of 2 and another cubed root of 2, right? Okay, because I need 3 of them. Okay, so now my denominator will be, I have 1, 2, 3 of them, that's 2, okay? But what did I do down here? I multiplied by 2 of those guys, so I really multiplied by the cubed root of 2 times 2 is 4, right? So that's going to be 5 times the cubed root of 4 on top, okay? Because this right here, this is the same thing as this, okay? Remember, if I have the same root, then I can multiply these two numbers. Remember that? We just did it 2 seconds ago, okay? So that's why the cubed root of 2 times the cubed root of 2 is the same thing as the cubed root of 4. It's the same root, so you can multiply those two numbers to get the 4, okay? All right, and then I needed 3 of them because the root was 3. If I had a root of 7, how many would I need altogether? 7 of them, and then I would put a 2 down here, okay? All right, so let's try it. Let's see what we can do. All right, so my first example is the 5th root, the 5th root of 7, okay, over the 5th root of 8. All right, now right off the bat, you're like, okay, we can't have the root down there. So here's the 5th root of 8. There's only one of them, so I need the 5th root of 8 4 more times. Now, you can do that if you want, but let me just show you a little trick. I recognize this number 8 as 2 times 2 times 2. That's 3 2's, okay? I'm trying to find a 5th root, right? I already have 3 2's with that 8. So how many more do I need? I only need 2 more. Okay, watch. I'm going to rewrite this. You'll see what I'm talking about. I have the 5th root of 7 over the 5th root of, now remember 8 is 2 times 2 times 2, okay? This is what I'm talking about. If you recognize those numbers, those perfect cubes, it's going to make your life a lot easier, okay? Now you don't have to do this, but you're not going to get a simplified answer at the very end of the problem, okay? So it's good to know this. So look, I need 5 of them. Right now I just have 3 of them. So watch this. I'm going to put the 5th root of 2 more 2's, right? Now I have 1, 2, 3, 4, 5. Guess what that turns into in my denominator? Just a 2. Okay, and then up here, if I put one of these down here, I also need to put one up here. The 5th root of 2 times 2, that's 4. Okay, the 5th root of 2 times 2 is 4. And now look at my numerator. I have the 5th root of 7 times the 5th root of 4. Since I'm taking the same root, it's going to be the 5th root of 7 times 4 is 28. Okay, so that's how those work. All right, let's do one more. I'll do one more of these guys, okay? Check it out. I have the 6th root, okay, of 81 over 4. All right, so now there's a couple ways you can do it. Notice here I had the 5th root of 7 over the 5th root of 8. Here I have the 6th root of 81 over 4, all in one, okay? We can totally work with that, okay? You don't have to. You could break it up into this if you want, but let me just show it to you this way. I'll just kind of extend this, right? All right, look, I have a 4. Isn't that really a 2 times 2? Okay. How many 2's do I need altogether? Well, it says I'm looking for the 6th root, right? So I need 4 more. So this 4 turned into a 2 times 2. I just changed it into that. So I need times 1, 2, 3, 4. Okay, now I have, look, 1, 2, 3, 4, 5, 6. We're good to go. That's going to turn into a 2 down here in my denominator, okay? Now, if I put 4 of them down there, then I need times 2 times 2 times 2 times 2. Okay. All right. And I'm always thinking of simplifying, okay? Now I recognize 81 as 3 times 3 times 3 times 3, okay? I'm trying to take a sixth root of that, right? If it's 3 times 3 times 3 times 3, that's only 4 of them. And then I have these 2's, that's only 4 there. So it didn't really work, all right? So I have 4 3's and 4 2's. I needed 6 of something. It just didn't appear. Nothing's there. So I'm just going to keep it as the sixth root in the numerator, sixth root of 81 times, this is 16. I don't know that. Let's try it. Can you see that there? Okay, 81 times 16. That is 1296. All right, so the sixth root of 1296. All right, it can't be broken down. Okay, I promise you, because if I was to put this in prime factorization, that would be 3 times 3 times 3 times 3, which is prime numbers, times 2 times 2 times 2 times 2. I don't have 6 of any of those. Okay, so 1296, that's going to be broken down as far as we can. Okay, all right, so that's that. Let's move on. Let's see, we have combining radicals and roots. So let's do part D. Combine radicals and roots. Okay. And here is my first example. I have the fourth root of 10 plus 7 times the fourth root of 10. Okay. Now, let me ask you a question here. Let me open the blinds. It's getting dark in here. Hang on. Watch this. Most people are just like, okay, show me what to do. But listen, let me ask you something. How many fourth root of 10s do you have right there? That's right, you have 1. How many of them do you have there? You have 7. So, how many do I have all together? If I'm adding them, you're right, I have 8 of them all together. So I have 8 of the fourth root of 10s. Okay, that one's pretty straightforward. Okay, not a lot going on there. Let's try this guy. Every now and then you'll see it written, here that was one example. Let's do another one. Every now and then you'll see it in rational exponent form. So we have something like this, 2 times 8 to the 1/5, that's the fifth root of 8, right? I have 2 of them, okay? Plus 10 times 8 to the 1/5, right? That's the fifth root of 8. There's 10 of them. There's 2 of these. How many do I have altogether? I have 12 of them. So 12, okay, of the 8 to the power of 1/5. Or I have 12 of the fifth root of 8. So you could write it like this if you want, 12 times the fifth root of 8, okay? Again, if I'm going too fast, remember, you write the radical, you write the base is 8, the power is 1, so you don't need to write a 1 right there, and the root is 5, so it's the fifth root, okay? All right, let me get another piece of paper. All right, let's get into some good work. You'll like this. Well, I'm being funny. All right, here we go. Let's try this example. We have the cubed root of 54, okay, minus the cubed root of 2. All right, now if you notice, they don't match. We have a cubed root of 54 minus the cubed root of 2. Well, here's the interesting idea. We're going to get them to match. If you see a cubed root of 2, you know there's going to be a 2 hiding in here. Okay, so watch this. I'm going to rewrite this as the cubed root of something times 2, right? Well, what times 2 gives you 54? I hope you said 27. And I don't know if you notice it, but 27 is a perfect cube. This is great, okay? This is still minus the cubed root of 2. Watch what happens. This is the cubed root of 27 times the cubed root of 2. You don't have to write it like this. I'm just kind of breaking it up to show you, okay? What's the cubed root of 27? I hope you're thinking 3, okay? If you're not, you need to join me for office hours. Okay, so we have the 3 right there, and then we have the cubed root of 2. And then it's minus 3, the cubed root of 2 again. So minus the cubed root of 2. Watch this. How many cubed roots of 2 do I have here? 3 of them. How many do I have here? How many am I taking away there? 1 of them. So now I have 3 take away 1. That's 2 of those cubed roots of 2. Okay. Let's try one more of those. Let's do one more. We have the third root of 5, okay, plus the third root of 40. Okay, obviously they don't match. Okay, we have the cubed root of 5. What number is hiding here? I hope you're thinking 5, because we have a 5 here, so there's going to be a 5 hiding there. So watch this. Write down the cubed root of 5 plus the cubed root of, it's going to be something times 5 is 40. That's right, 8 times 5. And look, 8 is a perfect cube. Okay? So you can write it like this, the cubed root of 5 plus the cubed root of 8 times the cubed root of 5. Okay? This guy right there, you should know it. That's 2. The cubed root of 8 is 2. So we have the cubed root of 5 plus 2 of the cubed roots of 5. How many do I have altogether? That's right, I have 3 of them. 3 of the cubed roots of 5. Okay? All right, and let's squeeze in the last little bit. I'm running out of time, less than 5 minutes. I will go ahead and do part E for you. It is variable expressions. Variable expressions. Let me sharpen my pencil one more time. So we have something like this. It's actually kind of easier, but again, it just depends on your skill level, okay? We have something like this. The cubed root of 64, okay, y to the 6th. Okay, again, it's really helpful if you know, if you recognize that 64 is a perfect cube, right? What times what times what gives you 64? It's 4. Oop, there's 4 right there. Okay, so watch. I'm just going to break it down like this. You don't have to do this, but so I can show you some sort of like systematic way, right? We have 4 times 4 times 4, that's 64. And y to the 6th, watch this, see if you agree with this. Y squared times y squared times y squared. Okay? Isn't that y squared times y squared times y squared? Doesn't that add up to y to the 6th? And look what we have. We need a cubed root. So anything that you see 3 times, okay, we got that, so that's a 4. And we have this, so that's a y squared. And we're done. Okay? See if I can do 2 more. Example. We have, let's do this. The 4th root of m to the 4th. That should be helpful. Okay, over n to the 8th. Okay. What I'm going to do is I'm going to just turn this into rational. Okay, rational exponents. Okay, so watch this. This is going to be m to the power of 4 over a root of 4, okay? And this is over n to the power of 8 over a root of 4. Watch what that turns into. This is m to the power of 4 over 4. That cancels into 1, so it's just m over. And then it's n, 8 over 4, that reduces to 2. So we get m over n squared. All right. I think I might have time for one more. Let's try this. Example. We have 14 x times y to the 1/3 over 2 times x to the 3/4 times z to the -6. All right. Now this might get messy. I don't know. I don't know that I've ever done this before. So watch this. I notice the 14 over 2. That cancels, this turns into 7, so I have a 7 right there, okay? Now watch this. I have x over x to the 3/4, okay? Isn't this x to the 1, isn't that bigger, the power bigger than this guy? So I'm gonna cross this off, okay? I'm gonna cross that guy off, and I'm gonna go with this guy right here, x. That's to the 1, which is 4 over 4, so that's gonna be x to the 4 over 4 minus that 3/4, okay? We did this with easier examples, okay? All right, and then we have a y to the 1/3, and we have a z to the -6 down here. I'm gonna bring it up to the top, so it's z to the +6, okay? And everything in the denominator is gone, it's just a 1. So now I have 7, and then this is x to the 4/4 over minus 3/4 is 1/4, so x to the 1/4. We have y to the 1/3, and we have z to the 6th. That was kind of a cheesy problem, but we're out of time. Love you guys, peace.